So good morning, everyone. My name is Enrico Cadau. I'm here on behalf of Ferran Gascon, who is the Sentinel-2 mission manager. So I'm working for the European Space Agency since 2009. So now we move back to Europe, and I'm going to present Cent2-like, which is a new processor we are going to develop to generate harmonized infused surface reflectance ARD products. So I slightly changed the title with respect to what was in the program. Here just a very brief outline of my presentation. So we will go through the main aspect of a Sentinel-2 mission, data products, and then we will talk more in detail about the Cent2-like processor and products. So Sentinel-2 mission, most of you already know about the STAR mission of ESA and Copernicus program. So systematic acquisition of land surface and coastal waters, high revisit frequency. Now we have 2 satellites flying, so 5 days of revisit time with the same viewing direction. Large SWOT, so almost 300 kilometers of SWOT on ground. Spatial resolution from 10 meters to 60 meters in 13 bands from the visible near infrared and also in the shortwave infrared. Free and open products for a large range of application. Long-term mission availability, so at least up to the 2030. Here you can see just a small Gantt of the first 2 launches in 2015 and 2017 for A and B unit. And then there are foreseen around 2023 the launches of the other 2 units, C and D. This picture shows very briefly the revisit time of the frequency of our mission scenario. So in red you can see all the land masses and also coastal areas and inland waters and seas, which are systematically acquired by 2 satellites. So the resulting revisit time is 5 days. In yellow, the areas which are currently being acquired only by 1 satellite. So the resulting revisit time is, of course, 10 days at the equator. Concerning mission products, so these are our portfolio. Level 1B, which is top of atmosphere radiance in sensor geometry. This is the, let's say, product which is not distributed to the public, so it's only for expert users. The production is systematic and the preservation is long-term. Then we have the level 1C, so top of atmosphere reflectance in cartographic geometry, distribution public, production systematic, preservation long-term, and then we have the level 2A, so surface reflectance in cartographic geometry, which is systematically generated worldwide since the end of 2018, with a preservation of 18 months of rolling archive. So the level 2A is, we can say that is already 99% CAR for Rail compliant. So, which is the context? As you know, there is a growing need from several applications of having analysis-ready data, providing surface reflectance measurement with frequent temporal revisit. In parallel, of course, there are also several optical image sensors which are already flying, and a growing number are planned to be launched in the coming years. So all these missions together would have a strong potential if they were to be combined in a single coherent data stream, able to provide consistent surface reflectance measurement with higher revisit frequency. So this is just a slide showing the main, let's say, companies, enterprises that are using systematically Sentinel-2 for smart farming application, agriculture, and so on. So in this context, the European Space Agency decided to develop a new processor called Cent2-like, designed to generate ARD harmonized infused time series of Sentinel-2 and Landsat 8 products. The first demonstration phase just completed. We are now approaching to phase 1, which will last 2 years. So it will start just after the summer break. And we will see also what it will include. So this is our, let's say, logo. It's very, yeah, Facebook-like. In the future, other optical mission will be also integrated in this processor. So let's go more in detail of what Sentoo-like is doing. So you can see this is a very high-level workflow. So you can see on the left, so the main input product. So we have Sentinel-2 Level 2A product, and Landsat 8 Level 1T. So you can see that most of the, let's say, processing steps are applied to Landsat 8 because it's, let's say, the goal to harmonize Landsat 8 to Sentinel-2. So harmonization includes consistent atmospheric correction, spectral adjustment, BRDF adjustment, and of course regridding. The future product will be called L2H, which stands for harmonized. So in this case, we will have Sentinel-2 at the native resolution, and Landsat 8 its own native resolution. And then there is another step which is called fusion, which will generate the level 2F, which stands for fused, where, let's say, this process will bring Landsat 8 resolution to Sentinel-2. So we will have two new ARD products, the level 2H, as already said, harmonized Sentinel-2 Landsat 8 product, where native resolution, spatial resolution are kept. You're just the, let's say, the bands which are foreseen to be generated, and then the level 2F, which stands, as already said, for a fused Landsat 8 to Sentinel-2 products, where the Sentinel-2 spatial resolution is, let's say, shared for Landsat as well. Processing steps. This is just a slide showing the main processing steps. I will go more in detail later on. So atmospheric correction. So the first prototype, which was for the phase 0 of Sentoo-like, adopted an atmospheric correction algorithm based on SMAC with solar geometry and viewing angles, meteorological information as auxiliary, let's say, data input. But in phase 1 of development, we will implement the atmospheric correction using Sentoo Core also for Landsat 8 or 9. As auxiliary data, we will also use the Copernicus Atmosphere Monitoring Services, the so-called CAMS auxiliary data. In terms of geometric processing, the development of the algorithm has been, let's say, in the phase 0, with the following assumption. I mean, it was assumed that the Sentinel-2 geometry was temporally stable with no correction applied. This is, of course, not always true, at least waiting for the implementation of the so-called refining based on the global reference image, which is will occur soon. So Landsat 8 data is then co-registered to Sentinel-2. So on the left side, you can see how, let's say, the different Landsat 8 data is located with respect to the center of the, let's say, of the image. How after the correction, using this Medisys tool developed by CNES, the French spatial agency, the data is almost perfectly co-registered. And this is very important, and then I will show you for the fusion algorithm. Concerning BRDF adjustment, we used in the first prototype the ROI approach. We derive parameters which are unique all over the world, derived from the MODIS data. So a constant BRDF shape is assumed with all, of course, the implications. And then, as a first step, there is also this buff process. So in order to normalize the different spectral responses. Now let's focus on the fusion algorithm. So in the first prototype, an in-house method developed by Telespazio France has been developed. So it is based on prediction and downscaling steps. First, so the prediction of Sentinel-2 surface reflectance at Landsat 8 acquisition date. So we will extract, let's say, the high frequency from the high resolution Sentinel-2 predicted image. So you can see the image in gray. And then there is the downscaling of Landsat 8 data towards the 10 meters of resolution using the Sentinel-2 predicted data at 10 meters of resolution. I don't know if it is visible how then, yeah, maybe there is another example here. So here it's Landsat 8 at 30 meters of resolution, which can be also seen as a level 2H, so it's the harmonized product. And here how it looks like when the product is fused with Sentinel-2. I hope it can be seen, how the resolution improves. This is another nice example. It's an animation of 1 year of data. So on the left side, you have the level 2H. So both Sentinel-2 and Landsat 8 data at 30 meters of resolution. And on the right side, you have the same images at 10 meters of resolution. Few words about validation. So all processing steps, which I showed you before, has to be validated. For instance, the geolocation accuracy with the objective to certify that the registration accuracy is within 0.3 pixel in multi-temporal. The atmospheric correction as well has to be validated by visual inspection, by comparison of surface reflectance, using, for instance, reference data on ground. The access of BRDF correction as well has to be validated, as well as the SBUF processing steps. So in terms of validation, here is just an example of how it could be validated. For instance, the impact of each processing steps has, of course, let's say, a factor in the quality, in the time series, and it can be accessed, for instance, calculating the normalized, the NDVI, basically. So in these graphs, you can see the triangle red and blue, which are Sentinel-2 NDVI based on Sentinel-2 data, and the red triangle are the same NDVI based on Landsat 8 data. So there is, of course, rooms for improvement. So here are just the results coming from the first prototype, but there is already a good agreement in terms of NDVI. Of course, there is a densification of the image, which is then the main goal of this algorithm, of this processor. Very briefly, conclusion and roadmap. So first, Sent2-like prototype processor enables the production of multi-temporal surface reflectance dataset with Landsat 8 mission as additional data source. In terms of processing, coding, generic flexible processor has been developed during the phase 0, allowing to plug different thematic blocks and test different processing configurations. All the thematic blocks that I showed you before can be activated and deactivated by command line or by configuration file. So you can play, you can play with all the different configurations. And it has been shown to build very consistent time series of vegetation indexes. In the second phase, which, as already said, will start just after the summer break, it is planned to consolidate the operational performance of this prototype with an orientation, of course, of a cloud installation, because of course it has to rely on the Sentinel-2, for instance, archive and Landsat 8 archive. And in parallel, there will be the Sent2 core adaptation to Landsat 8 then of course all the other methods, for instance, the fusion, the BRDF correction, etc., has to be improved. Then just before concluding my presentation, I would like to show this slide. So there will be a workshop in Erin in Frascati, so close to Rome in Italy, at the end of November. So it will be an open forum for presentation and discussion of the current status of future development related to CalVal of spaceborne, very high resolution sound and optical sensor. So it's like a LESI Europe style, let's say. The abstract submission deadline is the 20th of September, and here just the link, but you can Google it, so VH Roda, for more information. And this concludes my presentation. Thank you very much for your attention. Here you can see the classic fog of the bay. Thank you very much.
So we do have time for some questions.
All right.
Questions? Perfect. Just go to the mic. We have 2 mics here.
Yeah.
Go ahead, Matt.
All right. So, hello. Okay. All right. This works. All right. So, just to clarify, like I think I sort of skipped over that slide where you're talking about the correction of the spectral bands between Sentinel and Landsat 8. Like with the SMAC method, you're pre-computing the atmospheric tables and then creating the coefficients for the sensors.
Yeah.
But is the atmospheric model being run specifically for the Sentinel-2 bands and the Landsat bands separately, or is there some sort of post-processing correction to
the coefficients were already pre-computed. We used the CSVO coefficients, so computed before. We choose, let's say, this solution because it was very fast atmospheric correction at the end. So it took less than 5 seconds to correct atmospherically Sentinel-2 and Landsat data. So the idea was to harmonize, of course, the atmospheric correction between the two platforms. In the future, we are moving towards the adoption of Sen2 Core for both platforms.
We have about 2 more minutes, so maybe if people can be brief with their questions and then
Okay,
responses.
please.
You were next.
Thank you. I have a question about fusion. You showed us very clear, cloudless, shadowless images, which are, of course, easy to fuse. But what happens in case of clouds, or what happens more importantly in case of sudden change? For example, a field has been harvested or something like that?
Of course, there are limitations. For the time being, the algorithm of fusion is relying on 2 past Sentinel-2 images. Of course, if these 2 images are cloudy, the results could not be good. So the algorithm has to switch back in the past. But as you go in the past, of course, as worse is the result. So this is currently, of course, a limitation.
So in case of change instead of cloud, will the change be detected and the fusion not be applied there, or will the fusion just...
Actually, we tested with some fire scars,
for
instance.
example?
Yeah, and apparently it worked quite well. It worked very well. But we are still at the beginning, of course, of the development.
Okay, thank you.
Yeah, welcome.
Enrico, thank you for your presentation. So what's the metric of performance that you benchmark your system on? Because we've heard a few different, in one of the previous presentations, the system Force was mentioned. They seem to do something very similar. So,
well, all the, let's say, validation metrics are still to be consolidated. So for the time being, what we have done was just to qualitatively checked that, let's say, the fusion algorithm was not destroying, let's say, the radiometry of the images. But in the future, of course, there will be more effort in this important aspect, because at the end, the goal is to provide this data to, for instance, enterprises and users who are interested in exploiting this data for agriculture, basically. So, yeah, for sure.
Thanks.
Let's thank Enrico one more time. So I'd like to invite Chris Durell up.
And me, and Steve Schiller.
Oh, wow.
Yeah, I'm going first.
Okay, I've got this. These are your slides? No.
Yeah, those are the right slides
These are the right slides.
for the start with, yeah.
And then the next, so the second deck,
Just slide it over.
yeah. Okay. Use the button to project it there.
And you guys will have 15 minutes and then 5 for questions, and I'll give you a 3-minute warning.
Okay,
So
sounds
go
good.
to-
All right. Well, good morning still, I guess, here. So I wanted to take a little bit of a time from Chris to try to talk about some of the calibration work that we're developing at Raytheon and trying to make it more usable, accessible to the community. And what we're focusing on, of course, is the need for achieving ARD data sets, interoperability, data harmonization, where we basically want to get the sensor out of the equation. You need to, that's the importance of calibration, is to make it possible to have information in which the you're looking at just the properties of the targets of interest rather than trying to interpret it in terms of what the sensor's telling you. And so the goal is to achieve that and provide a measurable objective where you're actually getting more dense, more timely information that allows you to develop new products and applications. So that's and that should be a measurable objective in this. We've talked about the importance of calibration. It's been mentioned many times, so I'm not going to belabor it here. But it's just to recognize that, of course, a starting point in ARD is to have good calibrated data. As we know if you're familiar with the way vicarious calibration is done, traditionally it's been developed in terms of being able to calibrate a sensor based upon using what is referred to as a reflectance-based approach, where you have large extended targets that are characterized on the ground for surface reflectance. Then you use an atmospheric model and to try to interpret the signal or predict what the signal is for that surface at the sensor. And there's a lot that goes into that because there's a lot of things that contribute to the signal that you have to know about in order to be able to predict what the sensor radiance will be that you're calibrating to. You've got the not just the signal from the sun, but you also have the hemispherical sky that introduces a signal that you have to model. You've got adjacency effect and sky path radiance. All these things have to be added into that signal to get the right prediction. What we're trying to do is improve that because we've been able to get 5% absolute cal through this process, and that's been a great development since the 90s when this was really taken on as a standard approach. Trying to do better than that. And the way that can be done is to actually use a technique in which allows you to reduce the signal to just the solar component. And that's the use of specular reflectors that allows you to image the sun by the sensor. And basically it has the ability to turn your sensor into a sun photometer. That is, you're looking at a signal on the ground by imaging the sun itself. And you're using these reflectors that are with curved mirrors that allow you to control the intensity based upon simply the radius of curvature. And you can apply these through the full dynamic range of the sensor and also from sensor to sensor, depending on just independent of the GSD, be able to light it up in a way that allows you to predict what the signal is, introduce a known signal. This is a way of using intensity sources rather than radiance sources. And that's why it has some advantage here. The only thing you need to know in order to get an accurate at-sensor prediction of intensity and radiance is in terms of the atmospheric conditions, is just a transmittance. So it has some advantages to reduce a lot of the noise that's generally associated with that. But what it also adds is not just radiometric calibration, but the ability to do other things, like spatial characterization, because we're using point targets that allow you to characterize the spatial performance of the sensor. These kind of targets also create excellent geometric ground control points for validating your geometry. It also allows you to measure a full two-dimensional point spread function for the sensor, not just the long scan and cross scan directions to see if there's some asymmetry there or not. So what you want is a system that allows you to do a full image assessment and that allows you to determine what your product quality will be in the long run. So this specular array radiometric calibration system is one in which we light up the sensor with these convex mirrors, and it creates bright points on the ground, essentially stars on the ground, synthetic stars on the ground. They all look like the sun, and they all have the same spectrum because changing the radius of curvature doesn't affect your spectrum. It's an ideal neutral density filter, basically, in terms of that process. And so you can predict these at-sensor radiances that are going to show up depending upon the GSD, because these are intensity sources and they follow the inverse square law in terms of how bright they'll be. But it's easy to calculate where you will be in the dynamic range, knowing the properties of the mirrors themselves and the atmospheric transmittance. But also you can create point targets. So we divide it up into radiometric panels and then point target that allow you to do the spatial characterization in a lot of detail. And once you have these in your scene, you can also do image assessment and see how your processing affects the image quality along the processing chain. And so you've got targets that allow you to assess that, and you also can do a temporal characterization to see how it changes over your time, including the effects of variations in focus, stray light, and all those kind of things that become important. What's really effective about this approach, too, is that the targets all look the same, independent of the sensor. They look like just a star on the ground. And as a result, you don't have variations from sensor to sensor just because of the spatial resolution in terms of how to interpret what the signal, what the source of the signal is. And so you can have in the scene targets that light up Landsat, but also WorldView 3. And they're all using the same methodology, using the same kind of targets with the same spectral properties. And you just adjust the intensity by using different numbers of mirrors or different radius of curvature. And so there's a lot of applications that can be done. One thing that we were hoping to demonstrate here, but the satellite was not able to collect here on campus, but we did collect successfully last week, was out at our site, out at a site at our location where I set up a target to show that we can actually do an empirical line method calibration with this system as well. That is, you can use this information to actually calibrate the sensor from DN directly to surface reflectance by putting targets and known surface reflectance on the surface. And as a result, you can get a calibration independent of whatever your radiometric processing is, your atmospheric correction, and or you know what processing you're using to get your ARD product. This provides a way of validating, and as a result, gives you, as here you can see, the target itself provides a way of providing a target on the ground. Even though it's small, it makes it really easy to use because these are small targets. Normally you have to put out very large targets to be able to apply the empirical line method. But we have developed an algorithm for being able to convert the specular reflectance to an effective Lambertian reflectance factor. And so once you have a target in the scene and you measure the reflectance of the background just around the target, you can actually use it to calibrate the whole image if the weather conditions are stable and uniform across the scene. And so you can see here is the actual surface reflectance being measured, and the yellow dots there are the surface reflectance it's retrieved from a SkySat collect at the 4 bands, and you can compare it to what is actually what you measure. Here you can see a grassy area. It's very red, very deep green grass, and a ball field where some dirt, so you can compare the results. And you can see we were able to use the target in the scene to calibrate the image to at-surface reflectance. And this is the basis for many of your products, for your higher level products. And this gives you a way of validating those independent of the techniques that you're using. And then, as you can see, here's a WorldView 2 image that is converted from at-sensor DN directly to the surface reflectance using just a simple band math equation where the coefficients are derived from the targets in the scene. So this is an image calibration process, not a satellite calibration process, but this is just one aspect. We can do an absolute calibration of the satellite with the same targets as well. So there's a lot of versatility here. And so I just wanted to kind of present that for your information. And you can see one of these targets is out in the back room there that we use. And I'll give the rest of the time over to my colleague here, Chris, who you know, and
yeah. Okay.
thank you.
Yep. So thanks to Stephen. This has been his brainchild for many years. What I'm going to follow up on very quickly. Yep. Thank you. Is the small concept of calibrating the entire planet, which is what we want is a real-time methodology for doing this. We believe that the Spark technology, when applied with the sun, can obtain the PSF, give you the atmospheric extraction, and basically calibrate the image or calibrate the sensor. These are real-time stations that can be tasked and tracked. So basically, you tell us where your satellite is, we point at you, you get a look, and you go on your merry way. These are on demand, so you use them when you need them, and you don't use them when you don't need them. This is just a quick video, and what we did is took the planet constellation and a couple of other satellites and put it in here. It's kind of hard to see on this resolution, but there is one site which is located at our facility in New Hampshire, not the optimal location, but as the satellites are flying around, you'll see them go green, and that means they've fallen within the angular window for us to give them a calibrated look, and you can see how fast we can actually do this, minutes. We unfold, we give you a look, and we fold. So this, we believe, drives in a real-time, scalable, cost-effective means for calibration, radiometry, geometry, getting better metadata, and interoperability using this type of methodology. We believe that drives in harmonization across big sat and small sat. This same technology can be applied to airborne sensors, just as well as it can be applied to satellite sensors. So think about a system that could actually light up your airborne sensor at the same time it's lighting up your satellite, with the same radiometric accuracy in the same scene. Think what you could do with that. So now you get your high resolution and your medium or low resolution tied together in an absolute fashion. We're challenging the group today to think about what you could do if your calibration was tailored to your instrument and your GSD and your bands. if it was tied to the same accuracy as the big sats, if it was available when you needed it, and it could tie you traceably back to the airborne coefficients, and if it was a fractional cost. This is a subscription system, not a hardware system. So that means that basically we're looking at a pay-per-use type model, where you get as many looks as you need, when you need them, and that enables us to take the calibration as it is today, which is very expensive, perceived to be difficult, and generally, considered to be sort of an afterthought in the industry, and it puts it up front where you can actually, at low cost, or at cost that you can control, you can put this into your equation and determine how it affects the value of your product. These are some of the results that we took on last week. These are results that we took Sunday. We were going to deliver the results today. That was within 24 hours of actually receiving the imagery. We actually had radiometrically corrected data for that product. We didn't get the imagery, so I wasn't able to present that, but that's okay. I think that also plays into the message of what calibration has been. You can send people out into the field for 30 days and they can come back with nothing. Here, you can revisit this as many times as you want. You may get nothing on one day, but you're going to get it at some point. So we're asking you, we're going to be around. We have one of the systems set up back in the back room, and we're trying to start a discussion about how this could change the industry, what this might look like in terms of the commercial model, how you think it might affect your business model, and how the quality of the product you're trying to produce. And we'll be around to talk with everyone, and there's a short survey if everyone wants to scan the QR code. But thank you very much. That's it. Okay, one or two? All right. Any questions?
One or two quick questions. Go to the mic.
Yeah.
Hi, Chris.
Yeah.
So
Steven.
what's the limiting uncertainty in this? This is a really cool idea, but I would think one of the big drivers would be the RSR knowledge for the spacecraft.
I'm going to let Steven answer that.
Yeah, it's been demonstrated that we can achieve better than 3% absolute accuracy on a single overpass. And so over time you can beat the noise down and improve that a lot beyond that. So if we get the system that Chris has described, when we get it up and going, we'll hopefully be able to do better than that.
What assumptions go into the model for the actual customer result? I mean, what information do you take from them to handle an answer?
We need to know the position of the satellite, obviously. This is what we're trying to do, is to allow the satellite just to see the solar signal. And as a result, it's going to be a narrow field of regard in which we can light up the sensor. We need to know where it is, and also some information about the GSD of the sensor, its range and stuff, but with that information, we can provide an at-sensor calibrated radiance image for you to process.
Sure. Okay.
Yeah.
Last question, briefly.
Is this on? Yeah. Okay. So you mentioned that the one sort of variable left in the equation is the atmospheric transmission, and you said that it's sort of based on the assumption of a stable scene with consistent conditions across it, and I'm wondering how much of an effect, how you calculate the atmospheric transmission and how much of an effect it has in terms of, if you're correcting an entire scene, how far away from the actual calibration point can you go, and how does your uncertainty increase?
Yeah, we don't want to mix the two. There's two approaches described. The atmospheric transmittance is all you need to know in order to predict an at-sensor radiance, simply knowing the reflectance of the mirror and its radius of curvature. That is for a sensor calibration. In terms of the other approach, that you can, once the sensor is calibrated, you can then go back and use the same target to do this reflectance, this empirical line method approach that allows you to calibrate the image independent of you don't need to know the transmittance for that. All you need to know is the reflectance of the target on the ground. And that allows you to convert from at sensor DN to surface reflectance using the reference on the ground. That's what the empirical line method allows you to do. So there's two different techniques with different applications that can be used with these same reference targets. If they're available within the scene to calibrate the scene, or if they're available for an overflight in which you measure the transmittance and predict the ad sensor. You can ad sensor radiance. You can do either approach with the same targets.
But we invite you to come talk to us. Ask the questions back there. We'll challenge us.
Yeah, the area at which the empirical line method works has always been the case that it depends on the atmospheric conditions being stable, the same at the target as it is everywhere else in the scene that you're able to apply it to. If there's a lot of non-uniformity, it's for validation. It's not necessarily for more than that in its best application.
Great, thanks guys. I think this is a really interesting opportunity to have this as a service and a subscription. So our next and last speaker of this section is Norman Barker from TileDB. And so I'd like to invite Norman up. And I think you also have a co-presenter. And I'll let you introduce him. Here we go. Sorry.
So do I get to see my slides? Okay, hello. My name is Norman Barker. I've been working in the US for the last 12 years, and before that I was working in the UK. So I do have quite a British accent, so if you have a problem understanding me, come and grab me at the end and we can go through the presentation again. So I'm here to talk about the work that TileDB have been doing with Capella Space, about creating time series stacks of SAR data. And I'm going to start the presentation by telling you a little bit about TileDB before handing over to Scott to introduce Capella. And then we'll be going back to Scott at the end where he can talk about some of the more of the work that Capella are doing. So what is TileDB? TileDB is open source. It's a novel format and powerful storage library for storing and accessing massive, dense and sparse multidimensional array data. And so far we've been mainly talking about COGS, Cloud Optimized Geotiffs, HDF, NetCDF, and Peter Becker talked about MOF and CRF yesterday. But TileDB is a different approach. The TileDB storage engine is optimized for the cloud. By that, we mean that you can go and access S3 efficiently. And it was founded in 2017, but it's been in development for a lot longer than that. It was spun out of Intel Labs at MIT by my boss, Stavros. So far, TileDB has raised $4 million in seed funding, and it's been raised by Nexus Venture Partners and Intel Capital.
I'm Scott Sonnen with Capella Space. So we are building the first US commercial SAR satellite constellation. So we're aiming to do hourly revisit anywhere on the Earth and taking data at very high resolution. So our focus is really on reliability and timely delivery. And we have our first commercially operational satellite, which we're calling Sequoia, launching in January.
Okay, so we're going to go into what is TileDB, and we're going to go into the scope of the work that we were doing in Capella. So TileDB as a company have been investigating TileDB as a possible storage format for frequent revisit, multi-temporal analytics-ready SAR data stacks. In particular, we were developing an open source Python library for SAR analysis based on TileDB. And the reason why that is important is that even though there are quite a lot of SAR libraries out there, they're not always commercially license friendly, they're under the GPL. And we really wanted to publish a library under the MIT and make it a little bit easier to use, include some more documentation and tests, and just be able to increase adoption within the community. A lot of the existing libraries are single process, and we wanted to show how you could do that with a library called Dask. And the reason why I wanted to do that is we wanted to be cloud-centric and show fast parallel processing. We're currently using the public UAV SAR data for its evaluation, but that will be changing. And we're creating an analysis array dataset, which is a time series stack, so a time series cube of complex SAR data. So I think thought it was useful to define what is SAR. So SAR's been around for an awfully long time, but it's getting a more rapid adoption now. People are getting a better uptake because they're realizing that it's very, very good data. It goes through cloud, smoke, fog, and darkness, which you don't always get with an optical data set. I just want to show you how a SAR collect works. So you can see in this case it's a plane or a satellite, and it's going along an azimuth direction, and it has a range. So you can model that as an array in X and Y, and then you can go and geo-register it after that event. And as Scott was saying, Capella is taking SAR a step further, enabling hourly high-resolution SAR global coverage for government and commerce. So what are the features of TileDB? So I think the most important thing is that TileDB was invented and modeled on sparse arrays first, then that was extended to dense arrays. So what do I mean by a sparse array? Well, if you think of a point cloud, it's high density in a particular region, and you can extend that globally. And then for a dense array, we're talking about your typical raster data set, which has an even pixel resolution. Another feature that we have is that we can do rapid updates and appends on dimensions, and we can do that over the network as well as locally. Perhaps the key feature for our use case here as an analysis array data set is that we support multiple attributes for a single cell. So as well as having the complex value, you can also have your DEM value as well attached to that pixel. And we can do multiple dimensions, and that's very useful if you're talking about meteorological data, where you can have multiple variables for a particular model. We do parallel reads and writes for network storage, and to do that, we have a concept of a schema. So you create your schema for TileDB, and then you can go and write from multiple nodes to that particular array that is defined by that schema. In a way to improve adoption within the community, we have good APIs with Python, R, Java, Spark, Presto, Go. And particularly within geospatial, we've been writing format drivers for both Poodle, which is a LiDAR abstraction library, and GDAL, which I think you're all familiar with. We also support encryption at rest, which is kind of useful if you're doing government-based applications. But we're also cross-vertical, so not just geospatial, we also have applications within finance and genetics. We have timestamp fragments, and then at the end of your array, if you're not interested in those timestamp fragments, which gives you a bit more overhead, you can consolidate the array down to a single array. We are very well documented. If you go to TileDB.io, you can find all our documentation on the web. And we're under a commercial-friendly license in that all of our software is released under MIT license. So let's focus more on TileDB for geospatial data processing. We can model complex raster data with multiple attributes per pixel. And by complex here for SAR, we mean both amplitude and phase. And we model that as an array within an array, which is the common way of doing it with GeoDiff. We added a format driver to GDAL, and the idea was that we could use the GDAL tooling, e.g. reprojection, translation, to go from existing data formats to TileDB to increase adoption. Within GDAL, you also have this concept of sub-datasets, which is a model that's used by NetCDF and HDF. And you can use GDAL Translate, the tool, to go from an existing HDF dataset, a NetCDF dataset, and even NITF, to a TileDB array. We also support attribute labeling of values in the array, and that's important because you might have X, Y, and Z, but you might want to label one of those dimensions as temperature, for example, and you can go and access that array using that value. Then for SAR, for the work we're doing with Capella, we're creating a time series stack, and you can go and append in time to an existing array. So whatever features are available within TileDB, you can do a filtering operation before you write. And you might want to do a filtering operation to go and increase your compression ratio. So you might want to do a bit or a byte shuffle. And if you use the algorithm from BLOS, which is implemented in TileDB, you can add that shuffle filter before you do a compression. And that will increase your compression ratio significantly, for example, using CSTD. So I did want to talk a little bit about compression because I'm hearing a lot about compression within COGS and how that's important. And my background with COGS is that I added WebP compression to libGeoTIFF and libTIFF last year through GDAL. And that gave us significant savings and saved a lot of money per year for access. But I think compression can be a little bit misleading when you're talking about analysis array data sets because compression is more about your end use case. So for example, if you're using JPEG 2000 compression, you don't always need all the coefficients from that wavelet compression to go and do your analysis. So I'd say that compression should be dependent on your end use. Much more important is the size of your tile request or your byte range request to S3, in that you want to go and try to match your cache sizes to go and get optimum performance. But saying that, compression is still very useful if you want to save your storage costs, and TileDB supports deflate, Z standard, LC4, hourly, bzip2, and double delta. So within the TileDB API, we support two different methods of querying, both a synchronous query and an asynchronous query. And depending on your experience with programming, an asynchronous query is very similar to a futures API within Node.js or a promise, in that you submit the function, you can either wait for the return and then process the result, or you can just go and submit and then get the result back immediately. So Dask is a Python library that takes an array-like object. Could be Xarray, could be NumPy. It's written in Python, and it enables you to do parallel processing either locally or in the cloud. We modified the GDAL driver to support parallel writes to an existing TileDB array. So within GDAL, you create the TileDB array schema, and then from multiple nodes, you can go and write to that array. And that code's available in GDAL 3.0. Right now in master, Erin's working on supporting a new multi-dimensional data access API in GDAL, and that's modeled on HDF and NetCDF. And as soon as that code has been reviewed, we will add TileDB support for that. So for the work we're doing with SAR, we're going to show you how we did SAR computations in parallel using Dask to a TileDB array on S3. Okay. So GDAL is going to be supporting multi-dimensional access, but you can also go direct to TileDB and get the values such as height, latitude, longitude, and also the complex value. So this is actually Dask running. If we had access to SSH here, which we haven't, unfortunately the port is blocked, I'd have showed you this running live. But here we have a job submitted across 4 cores that was running on AWS. So you can see the 4 cores there. And a job in a single process would take about an hour. We're able to get down to about 10 minutes. So I said at the beginning of the presentation that one of our objectives was to make this very easy to use. And quite a few of you here probably have experience with GDAL, and it isn't that hard, but there's still quite a learning curve. We want to remove that learning curve so that scientists can just go and do their processing. And one way of doing that is to use the Rasterio library, which is an easy-to-use Python library based on GDAL. It comes with a whole bunch of tools, including STAC tools and cog tools, and we added a STAC-SAR tool to Rasterio. And you can see here that we added a despeckle function, and the despeckle function actually delegates that to Dask, which includes the despeckle library. And then we said you could go and say which bands of a particular SAR stack you wanted to process, as well as specifying the tile size, the number of workers, and the number of threads per workers that you wanted to use. So that's going to be public, an MIT license, and it will be published to GitHub. So let's talk a little bit more about the implementation of the coherence change detection algorithm that uses Dask. So within Dask, you have this API function called map blocks, and also another function called map overlap. And why is that important? Well, when you have an ARD, you're breaking that ARD into tiles, and you can have tile artifacts when you're putting an algorithm over an ARD. So map overlap will extend your algorithm slightly over the next tile boundary, and then go and consolidate that back at the end. For the algorithm that we're using, which is a mean and variance window approach, we only needed to use map blocks. Okay. So what were the challenges? Well, the first challenge was supporting complex data types. In that traditionally it's only been supported in TIFF, kind of supported in HDF, and a few other proprietary formats, and we needed to add that into TileDB. We then needed to make this very easy to use, so we added this to GDAL. And this is quite a huge format driver to add to GDAL, and that took a couple of months of review. And then we also needed to make sure that we could go and support geospatial registration within TileDB. So when you query a TileDB array, which is normally X and Y, that you get latitude, longitude, or whatever projection you're intending to use. So SAR data is large, and when you create a temporal stack of SAR data, it's even bigger. And it's going to get even bigger the more slices that you add on to the end of your array. So we really need to be able to create this file structure from the get-go and then be able to append as you did each collect. When your data gets very, very big, it's very, very hard to render. So we needed to subsample prior to rendering. And then perhaps the hardest thing for me is, even though I have a background in remote sensing and mathematics, I haven't done a whole bunch of SAR. And there isn't that much SAR tooling or algorithms that are out there. So we needed to go and lean on Capella to go and validate some of our methodologies. And then software licensing, I'd like to have included a few other existing SAR tools, but they're licensed under the GPL, and we need to make sure it's commercially friendly. We touched a little bit about optimizing performance, and there's something to come back to. So by default, because people are doing mainly web maps right now with ARDs, you get a 256 by 256 tile size, or you get a 512 by 512 tile size, and really you need to be optimizing that for your local cache. 1 minute, well, okay. So let's go through a bit faster because I'm running out of time, Brexit. Coherence change detection, so lots of theories. For noise and clutter, you can assume a Gaussian distribution, even though it's a Gaussian shift. And we're detecting mean and variance between two registered images. And this demonstrates unique features of TileDB, of reads and writes from S3, as well as tiling and multi-temporal support. We're currently in testing with UAV real test data sets. And here's a synthetic example. So you can see I have a noise distribution on the left based on Gaussian. I introduce them across, and I can detect across using that algorithm. And then I'm going to show you the Jupyter Notebook, just to show how easy to use the Python API is. And then we took an image over Hayward's Fault, which is a fault line in California, and it showed that from 1 year to the next, we had a significant shift in time, and we had to detect that deformation. So differentiators, multi-dimensional support, append and update, as well as parallel processing and tooling around these areas, and all of this is going to be open source. I want to quickly talk about COGS before handing over to Scott. In that COGS can be a bit of a data management headache, in that you have an instance in time within a TIFF file, and they're typically managed by something called a VRT file, which is a text file, and all that metadata indexing is built inside TileDB. Our current state of play with TileDB and ARDs is we have implementation in GDAL, as well as within Poodle, and we're implementing coherence change detection with a review by Capella.
So I just want to quickly talk about what we're going to be doing over the next 12 months or so to make SAR data more accessible. So my big goal is to get very high resolution SAR data into the hands of as many data scientists and engineers as possible in the next year. So our first step towards doing that is we are flying an aerial campaign over Rotterdam. We're collecting hourly, very high resolution SAR data. We're going to be making that available on our forthcoming data platform, which is STAC-based for some of the API. The data will be available as cloud-optimized geotiffs there. It's also going to be processed to the Capella product spec. We are interested also in exploring new ways to make these massive multi-temporal data sets available as ARDs in ways that are easier for the community to work with. Hence our project here with TileDB. We think that's a really interesting way to make this data available. I want to mention that the data from this preview will be available for free and under an open license. All you need to do is sign up for our platform to access it. We'll be making it available also through some other venues that we'll talk about later. And our big focus for this data set is to see new applications developed with a focus on data fusion, change detection, and object detection as well. And I just want to leave you all with a quick preview of what Capella data will look like to try to show you that SAR is not scary, SAR is not counterintuitive. So this is just an end-to-end test of our radar payload that we flew recently over California. Thank you.
Anybody have a quick question for these guys?
dumb question. That's SAR and that's RGB?
Yes. Optical on the right, SAR on the left.
There are no dumb questions. Anybody else? Great. Well, I think, let's thank these guys one more time. And actually, I would invite Scott and Norman, don't go too far, so I would invite the speakers from this session, Enrico and then Scott Gish, to come back up for our last panel. And I'm going to try to make up some time so that we get to lunch and get our almost our full hour for lunch. So I'll just go ahead and get started while the panelists are coming up. My name is Erin Robinson. I'm the Executive Director of ESIP, which is, you guys can just sit in the chairs, the Earth Science Information Partners, and it brings people like you all together around common data challenges like analysis-ready data. And what I've been seeing lately is that this combination of the tech-savvy community plus the data is really doing a lot of interesting stuff, and I think that the last day and a half has shown us some of those things. So just as a quick intro to me, I got started doing long-range transport of smoke and dust. I was processing CWIFS data. I don't know if anybody remembers CWIFS prior to MODIS, and deriving aerosol optical thickness to try to tell a story about smoke transport. And, you know, we've heard this over and over again this morning, so I'm not going to dwell here, but there was a lot of kind of Sisyphean activities of the pre-processing of the shopping cart of find, access, use, and understand, just to get to the really interesting part of doing the science. And I think that one of the things that I've seen over the last 10 years is that we're speeding up that time to science. So we're just going to keep on going. So there's been, in the data management world, there's been a lot of talk around FAIR, which is findable, accessible, interoperable, and reusable. And I'm not going to dwell there, but there's this statement that comes out of that paper that there's a need to improve the infrastructure that supports the scholarly reuse of data. And I don't really think there's an infrastructure problem so much as there is this global infrastructure problem. So this is where I would like to maybe kick off the panel with a question to you all about, I think all three talks shared some things that were reusable components. We had subscription-based CalVal, TileDB, and then the combination of Landsat and Sentinel. So I wonder if you guys could talk just a little bit about your perception maybe of this, how you've been collaborating and the challenges around collaborating with this community. And I think we have a mic. Or we'll just pass this guy. Anybody want to kick it off? Enrico, maybe the Landsat USGS? I think that's a success story.
Yeah, from my perspective, I mean, at ESA, it's been a while that we are, let's say, putting in place collaboration between agencies, between, let's say, private companies, so bringing together the requirements coming from, let's say, the main users, which are, of course, then the main drivers. Above all, in the last, I would say, 5-6 years, so even not specialized users as it was in the past. In the past, I mean, remote sensing was only for super, let's say, specialized scientists, which have basically driven products format, products projections. So all details were driven by a very small community.
Yep.
But in the last, let's say, years, we are, let's say, trying to accommodate it. Also users which are not very specialized, so common users, private companies. So all people that might be interested in making a business and take benefit from the remote sensing as such, I mean.
Yeah, so I think that's a good point. I wonder maybe if we can jump down here to common users. Are there common users on the CalVal side?
Yeah, so first just on collaboration real quickly. Yeah. So for us, being basically an instrumentation company who was calibrating assets on the ground and putting reflective materials on satellites, you know, we had to collaboratively work with Raytheon on their intellectual property to try to bring a product to this audience. So hopefully the collaboration is, and how do we engage with you on validating that and bringing that to a commercial model. What was the next part you wanted?
If there's a you talked about the subscription model for
Yeah.
CalVal, and I think Enrico was just saying that, there was some common users, they're seeing that kind of the way to collaborate has been there's some commonality. So I was wondering if you're finding that sort of baseline commonality. for CalVal.
We're seeing interest in it. So that interest in collaborating could be use of a site. It could be help with analyzing some data that people have. So even in the flyover that we did just the other day, there's a collaborative nature in trying to prove that out. So we're actually looking for the community in ways that you want to be involved. So we'll be in the back later.
Yeah, nice. So I want to go to TileDB. I think one of the things, Norman, that you mentioned was about licensing of software, and I think that that's something that often gets overlooked in the collaboration space, but I wonder if you want to say just a little more on licensing.
Yeah, I think there's two issues there. There's both licensing and format adoption. We're very grateful to Capella for even trying TileDB. The barrier to get a format change is significant in this industry, and it's not the same in other industries. So we need to try and change that somehow, and this workshop's a great way of doing that. I think in terms of licensing, I have nothing in particular against the GPL, being a free and open source software developer, but it isn't particularly helpful when you're doing commercial software. So trying to pick a license for your application if you're a scientist that allows other people to pick it up and improve it and contribute back is a significant thing to do.
So maybe just being conscious of, trying to build the connections here, I just want to ask the panel one more question, and that's, where do you hope that your work is in the next year, and what do you think that community, this sort of community, could do to help you get there? Norman, you're holding the mic, or let's go to Scott. Scott, have you said anything?
I think one of the challenges for us in SAR related to ARD is there hasn't been as much discussion about what ARD is for SAR as there has been in the optical world. There's some really interesting things that are going on at CEOS in Australia as well. But I think that the level of discussion is maybe a little less mature than in the optical world. So I think getting to a point where there's some consistency in terms of standards or best practices for ARD and SAR would be great.
Cool. Enrico?
Yeah, I can say that as already, let's say, anticipated, in the past, space agencies were, let's say, were driving, let's say, the users. Now I think it's the other way around. So the users are so many that we have to anticipate them, but we cannot anticipate all the needs of the user. So very often we have to adapt. We have to adapt to the user needs. Yeah.
Absolutely. Yeah. Scott, last word? Or actually, Scott and then Norman.
Yeah, I think the way that people can get involved is we're certainly considering seven-figure investments in assets and trying to do things for the community, but we have to understand from you what is the business model that works for this community. And we're hoping that's something that's a little more radical. It's a smaller pay-per-use instead of big upfront capital investments are a viable model. And so helping to understand the business model that works for all of you would be important.
Okay. So for me, it's more about just looking at different formats for your data and just looking beyond COGS if you're doing multidimensional or time series data. Have a look at TileDB, have a look at HDF, have a look at other formats. Okay. And that should actually improve all our work as a community.
Nice. Well, let's thank our panelists. And I think that I would like to leave you guys with this question when you go into lunch of where do you hope that you are in the next year, and what can this community do to help you? And I think that'll be something that helps propel us forward collectively so that we have things to report back next year. So thanks so much, Hamid, and everybody for the opportunity.
Thank you.